Okay, so last time we looked at a recurrence relation, okay, which is where we can use the plug and chug method. Okay, so for today we will be looking at a form of a recurrence relation, okay, which is linear recurrence relation of a certain degree, okay, and we will try to look at how to solve those types of linear recurrence relations. Okay, so a linear recurrence relation is a recurrence relation of the following form. No? So a sub n is equal to a constant c sub 1 times a sub n minus 1, which is basically the previous term, plus c sub 2 times a sub n minus 2, and so on and so forth until plus c sub k times a sub n minus k. So the c sub i's are real numbers. C sub k is not equal to 0 for the purpose of specifying the degree. Okay? Because if c sub k is equal to 0, then that would just be of degree k minus 1. Okay, so that's just really to set the degree of the recurrence relation. And do take note that because c sub i's can be any real number, they can also be zero. No? So they can be zero, and you can have, let's say, a constant times a sub n minus 1, and then you don't have a sub n minus 2, but you have a sub n minus 3. Okay, so those are still linear recurrence relations. So they are linear because this right-hand side, okay, is basically just a weighted um, values of the previous terms. So you can take a look at the c sub i's being weights, okay, of the previous terms. No? Um, and there are no expressions involving n, okay, and there are no powers, okay, involved in terms of the previous terms. Okay, it's homogeneous, okay, because no terms on the right hand side, okay, um, that there are no terms, okay, on the right hand side that are not multiples of the previous term. Okay, so meaning we don't have something like a plus 2, a plus 2 constant here, or a plus an expression involving n or some other variables. Okay, it's of degree k, specifically because of c sub k not being equal to 0. Okay, so we have that term, and we have constant coefficients. Okay, meaning the c sub i's here, we don't have, these are just constants, okay, and we don't have any expression involving another variable or even the variable n. Okay, so we don't have that. So that's what we mean by a linear homogeneous recurrence relation. All right, so from there, um, what we would now have is, let's say, in terms of classifying recurrence relation, um, so we have the following. No? Um, if you look at the expression, so this one, the first one is not a linear recurrence relation because we have a square for the previous term. The second one is also not a linear recurrence relation because we are multiplying expressions from the previous term. Okay. The, the third equation, so that's a sub n is equal to a sub n minus 1 plus a sub n minus 2. So that's a linear, homogeneous linear recurrence relation. Same thing with the fourth one. The fifth one is not a linear recurrence relation due to the multiplier of n. So that should only be a constant. Um, the next one is also not a linear homogeneous linear recurrence relation because of the plus one. Okay, so all the terms in the right side should be an expression involving the previous term. Okay, and the plus one here does not involve any previous term. Uh, the last one is a homogeneous linear recurrence relation because on the right hand side we only have expressions from the previous terms. Okay, of course we note that from this expression, the last one can actually just be written as a sub n is equal to 1 times a sub n minus 2 plus sorry, a sub n minus 1 rather, plus 0 times a sub n minus 2, plus 0 times a sub n minus 3, plus 1 times a sub n minus 4. Okay, so um, take note that, let me emphasize that since the c sub i's can be any real number, then they can be also equal to 0. Okay, so we have those expressions here. All right, so from this one, so what would now be our approach for the general solution to the problem? So we have this linear recurrence relation, okay? And then we will assume that a form to this, the general solution would be a sub n is equal to r to the n, okay, for some particular constant r, okay? So if this is the case, then we can rewrite the original linear recurrence relation in the form r to the n. So that's going to be the a sub n becomes r to the n. A sub n minus 1 becomes r to the n minus 1 based on this definition here. And then a sub n minus 2 becomes r to the n minus 2, and so forth until r to the n minus k. Then what we will do, because all the terms here has a factor of r. Okay, specifically, each and every one here has a factor of at least r to the n minus k. So this expression here, r to the n minus k, is a common factor, okay, for all the terms. Okay, so we can well, of course, we know that r would not be equal to 0, because if it's equal to 0, then that's just the trivial case, no? So a sub n is always equal to 0, no? So if we divide everything by r to the n minus k and transferring all the terms to one side, to the left-hand side, and making the right-hand side to be equal to 0, then we would get this expression. Okay, so r to the n divided by r to the n minus k would become r to the k, and then minus c sub 1 times r to the k minus 1, and then so on and so forth. So we have a decreasing power of r until we reach c sub k. So that turns out to be now a constant. So the good thing about this is, instead of having a recurrence relation, okay, in our as our equation, we now have just a polynomial in terms of the variable r. Okay, and we call this um, corresponding equation, or corresponding polynomial to the given recurrence relation as its characteristic equation. Okay, so essentially the characteristic equation is the equation that relates to the given recurrence relation. Okay, now because we now have a characteristic equation and it's a polynomial equation, okay, we can solve for the roots, okay, of the characteristic equation. Okay, and the roots that we will get from the characteristic equation are what we call as our characteristic roots. Okay, so we now have our characteristic roots, and the characteristic roots will now become important when solving our recurrence relation. Okay, so what would be the general form of the solution, okay, to this type of linear recurrence relation? Okay, so before going into the more general case, we look at first the second degree linear homogeneous recurrence relation. So that means we only have until plus c sub 2 a sub n minus 2. Okay, so suppose that we have this expression here. So uh, the corresponding, so in this case, the corresponding uh, characteristic equation for this expression. So this one, so let's just try to write it. So if we let a equal to r to the n, so this would become r to the n is equal to c sub 1, r to the n minus 1, plus c sub 2, r to the n minus 2. Okay, and then dividing by r to the n minus 2, we would get, and then transferring everything to one side, we would get r squared 1 times r minus c sub 2 is equal to 0. So this one is now our characteristic equation. Okay, and this characteristic equation, because it's quadratic, then we can have uh, either there are no roots, okay, there is one distinct root, okay, one root, okay, for this one, or we have two distinct roots. Okay, so we will look at different possibilities now. If the first one is that if the characteristic equation has no roots, okay, has no real roots, then the linear recurrence relation, okay, has no solution. Okay, so has no solution. Okay, so meaning there's what we mean by no solution is that there is no closed form, okay, for that recurrence relation. Okay, um, if we have two distinct roots, okay, so we will start with two distinct roots, and then later on we will have just one unique root. So if you have two distinct roots, so that means we can have R1 and R2 as our distinct roots, okay, to the quadratic equation, okay, which is the characteristic equation, quadratic characteristic equation. So you would have R1 and R2. And the form of the solution, okay, so this is the theorem, and we will not anymore prove this, okay. The form of the solution to the second degree linear homogeneous recurrence relation is given by this. Okay, is given by a sub n is equal to some constant b sub 1 times the first characteristic root raised to the n plus b sub 2 times r sub 2 raised to the n. So your task now is to be able to determine b1 and b2, and we can easily get this by using the initial conditions, okay, from the problem. Okay, so we will look at a step-by-step method for this one. Let's, okay. All right, so let's start with this equation. No? So a sub n is equal to a sub n minus 1 plus 2 times a sub n minus 2. Okay, where a sub 0 is equal to 2 and a sub 1 is equal to 7. Okay, so let me go now to the whiteboard, okay, so that I can solve this equation from the start, no? So that we will not be, and then you can just go back to the slides as a reference later. Okay. So let me now share the whiteboard. So let me just, so that's 11227. Okay. Okay, so you should now be seeing the whiteboard at this point. So let me just, okay. So So what we have is that from the original problem, we have a sub n is equal to a sub n minus 1 plus 2 times a sub n minus 2, where, let me just check. Wait. Okay, so okay, where a sub 0 is equal to 2 and a sub 1 is equal to 7. Now note that for our purposes, we will now start our starting index at 0. And there's a purpose for this. It will actually make the solution quicker, okay? Because one of the equations, one of the indices would be equal to 0. And in any case, pwede nyo namang i-shift na lang yung index. Okay, so you would still be creating the same sequence. So if you want to rename the index, the first element to be index 1, then that's fine. But in terms of the general solution, so we'll start with index 0 first. Okay. So for the first problem here, I will first do it step by step. Okay, and then we can skip some of the steps actually later as we go along. And as we look at more problems. So for the solution, okay, again, I will do it in the step-by-step form. Okay, so we set our a sub n to be equal to r to the n. Okay. By doing so, we will now be getting r to the n is equal to r to the n minus 1 plus 2 raised to the r to the n minus 2. We divide both sides by r to the n minus 2, giving us r squared is equal to r plus 2. Okay. So we would now have r squared minus r minus 2 is equal to 0. Okay. So let's just pause for a bit at this point and emphasize that this one, okay, so that expression here is what we call now as our characteristic equation. So this one would now be our characteristic equation. So let's call this as our CE. Okay. Now, what we will do is from the characteristic equation, we will factor it out. We will try to find the roots. Okay. So this one, r minus 2. So that's r minus 2 times r plus 1 is equal to 0, which means that we would have and then r sub 2. Okay. So r sub 1 is going to be equal to 2 and r sub 2 is going to be equal to negative 1. Now, one common question here is that, sir, what do we know when